So in our earlier lectures, we have seen what are nanotechnology, what are the applications of nanotechnology, how they are being fabricated, and how they are being characterized. And we have seen the characterization tools for the fabrication of characterization tools after the materials have been fabricated using different coating techniques, And later we have seen what are the applications of nanotechnology, and we have seen what are the military applications of nanotechnology and nanoscience, and in what way this nanoscience and technology is useful for research and development. Right. In today's lecture, we will see what are the basic uses of nanotechnology. What is the use of this nanotechnology? Right. So, uses of nanotechnology. See, uses of nanotechnology, as we have seen, they are used in the military applications. You have seen in our previous lecture. So, uses of nanotechnology in the military. So, in military applications, right? So, the use of this technology will be imparting to enable the technologies, right? Small, lightweight, incredible performance platforms, and we have systems and subsystems, and we have evolutionary and revolutionary military applications. Right. So in enabling technologies, micro or nano fabrication, we have the fabrication of materials, so coatings and the devices, right? So devices, whereas in visualizing the molecular level, so materials are being visualized to visualize molecules naturally. So how they are being visualized naturally, and what is the synthetic form, and how they are synthesized, how the materials are being synthesized, and what are the biomedical applications. So what are the applications? So these features have enabled the technology of using this particular of this particular science to a very large extent, right? So when we speak about the small, lightweight, incredible performance platforms, so we have some materials and devices, right? In materials, we have armors, fuselage, textiles, and energetic materials. And when we see in the case of devices, we have MEMS, that means microelectronic and memory devices, right? MEMS device. And we have the actuators and sensors, and we have some optical features, and also we have the device making on lab on a chip. Right. Whereas in case of computers, this use of nanotechnology will be used for processors. They are going to be used for displays, peripherals, and input-output devices. Right. So in case of sensors, we have the pressure sensor, chemical sensors, and biological sensor. Whereas when we speak about the systems and subsystems, they are used for guidance and control, and they are used for power systems. They are used for propulsions, signature control, intelligent materials of self-heating, and we have some military vehicles, right? Unnamed military vehicles and robots, and armaments, command and control, soldier welfare, human performance. So these are the evolutionary and revolutionary military applications. So in case of enabling technologies, micro or nano fabrication, materials, coatings, devices, and whereas in visualizing the molecules, we have the natural, synthetic, bio, and whereas in case of materials and devices, the armor and fuselage, and whereas in case of devices, we have the actuators, MEMS devices, and optical devices, and lab objects, and structures called membranes and electrodes, and processors, display, and peripherals, where peripherals are input-output devices, and we have certain lasers also. Right. Whereas in case of systems and subsystems, we have the guidance and control, power systems, propulsion, signature control, and intelligent materials, self-heating, military vehicles, unmanned vehicle and robots, armaments, and command and control, and soldier warfare, and human performance. So these are some of the uses of nanotechnology in the military sciences, right? So military vehicles, right? When we speak about the military vehicles, so their operability, so they are improved speed, and they have the maneuverability, range, and fuel economy, and lightweight nano composite structures, and miniature of devices or MEMS, examples like actuators, and nano coatings and self-morphing or reduced morphing for reduced drags, right? And new propulsion materials and systems. Whereas in case of flexibility users, we have the platform for modular vehicle design, and support for upgrades, longer life for materials and systems, and we have the enabling technologies, fly by light or power by wire, fly by thought, that is brain activity, head movement, eye movement, voice sensing, and survivability. We have the stealth material and systems for reduced signature, built-in sensor network for structural health monitoring sensor, and systems for poor weather controls. And when we speak about the maintainability, we have the miniature cards, right? Components of devices, actuators, and sensors, replacing hydraulics with electrical and optical devices and power, and improved paints and coatings, including paint removal technologies, structural prognostics, and health management material. So these are some of the maintainability features in military vehicles. So that means operability, flexibility, and survivability and maintainability are the very important uses when we use military applications, especially in case of military vehicles. Of course, the enabling technologies by fly-by-light, so power by wire and fly-by-board, that means brain activity, head movement, eye movement, and voice sensing are the latest technologies, enabling technologies to incorporate in military vehicles, right? So these are some of the uses where we can use unmanned vehicles, right? Robots, so that like robots which generalized for artificial intelligence, right? Battlefield robots, friend or foe, that means a friend or enemy can be recognized, and underwater robot for mine clearing in shallow water. So this was taken from Northern University, and we have fractal shape changing robot. Fractal change robot can affect a change in the shape of the robot structure. So we have micro unmanned air vehicle with motors, linkages, video camera, and an upload link RF communication receiver and antenna, that is intelligent automation, right? So these are some of the unmanned uses where nanoscience and this technology can be incorporated for unmanned vehicle or robots, right? So we have some armaments. So we have lethality, and we have survivability and accuracy. So when we have lethality, we have smaller, lighter weapons, systems that are more mobile, have longer range and increased velocity, from higher strength, lightweight structural materials with reduced aerothermal dynamic erosion, more powerful energetic materials, improved sensing or target detection capabilities, sensor protection from military applications and environmental threats, smart materials to control impact and weapon functions, and new fabrication methods for unique capabilities, for example, controlled fragment warhead. Whereas in case of survivability, we have reduced chance of accident from energetic materials that are less sensitive to environmental conditions, handling, and storage. So when we speak about accuracy of this particular armaments is very huge. So that is what better computers and electronics to process more information less time, and we have smart imaging sensors. For very precise target selections, environmental sensors for global weather data, and these features enable the technology to grow, to incorporate more on the armaments and also for military vehicles. So the best features is survivability. That means there is a reduced chance of accident from energetic materials that are less sensitive to environmental conditions and handling and storages. And at the same time, we have accuracy, better computers and electronics to process more information in less time, start imaging sensors for every very precise target or selections, environmental sensors for global weather data. So these are some of the uses of armaments. When we speak about the command and control, we need to first focus on the operability and the information, right? So when we speak about the operability, low-cost miniature devices and systems, making command and control more technology and economically efficient. For that, we use computers, electronics, imaging, wireless technologies, or unmanned vehicles or robots, or nano picosats, right? So picosats. So these are the main operation conditions for command and control, especially in military vehicle or for military applications, right? Low cost miniature devices and systems making command and control more technology and economically efficient. Computers, electronics, image, wireless technologies, unmanned vehicles or robots, nano picosats. So at the same time, we have the one more important parameter called data security. So this data security is being incorporated in this technology by the method of quantum computing. So quantum computing for encryption, that is what we tell, quantum computing for encryption. So when we study about the information, when we need to about the information, we need to understand the low cost real time sensors operating 24/7 in remote applications, high sensitive multiplexing chemical and biosensors for early warning of CB threats, right? Acoustic sensor for tracking noise emitting targets, miniature cameras, and electro-optical sensors for improved and smaller night vision devices, right? So these were the information, data security, and operability are the three important features for the command and control of the military vehicles, right? We're using this type of technology. That means low-cost real-time sensors operating 24/7 in remote locations, right? So high-sensitive multiplexing chemical and biosensor for early warning of CB threats, 3B threats, and we have acoustic sensors for tracking of noise-emitting targets, miniature cameras, electro-optical sensors for improved and smaller night vision devices, right? And whereas in case of soldier warfare, so we have the mobility, stealth, flightability, lethality, and survivability are the important features where soldier warfare are used, right? So when we speak about the mobility, the light multifunctional materials and systems for load reduction. For road reduction, 1000 lb to approximately 30 lb integrated power data bus antennas are required, and form-fitting uniform and waste elimination. When we speak about the stealth materials for reduced signature, active camouflage, flightability components for a multispectral vision system, audio system and voice control, and lethality components for modular weapon system, advanced laser systems, and advanced sights. So when in case of survivability, multifunctional combat suit with devices and material for ballistic protection, NBC protection, thermobaric protection, laser light protection, micro cooling and heating, and hydration system. So these are some of the important features, some of the important applications, and some of the important uses of technology, especially in the nano mode for solid warfare. So human performance and well-being. So survivability, that is low-cost multiplexing sensors for the rapid detection of NBC threats, low-cost portable medical devices for field use, new drugs or drug delivery systems, and intelligence, that is variable devices and implants for biomedical monitoring and psychological monitoring, and automated self-dedicating and genetic testing to determine disease and stress susceptibility factors, performance enhancement, devices for improving vision, hearing, and other senses, and MEMS devices and tools for increasing strength, automated injection system for the delivery of medications. When you speak about the repair, so miniature implantable medical devices, for example, defibrillators, MEMS assisted prosthetics with improved biocompatibility, improved technology for restoring vision, hearing, and other senses, smart surgical tools and systems. So these are the repairing materials for human performance and well-being. So what are the implications? The implications of military applications for DRDC and Canada, right? So we have mainstream industries present major opportunities for nanotechnology innovation, including national security, right? So US GDP in the year 2002, it was approximated to $10,446 billion, right? So that is, so for business or household consumption, the $703 billion, and business and household investments, $1,593 billion, and government consumption around $1,972 billion, and adjustment to exports and imports, etc., is minus $422 billion, right? So this has been incorporated. Business holder consumption is being for energy, and energy, the dollar around is 332 billions, and whereas for information processing is around $400 billion, and for motor vehicles $376 billion, and around transport equipment it is around 148 billion, and for national security we have $447 billion, and for medicals we have around 1148 billion. So these are all the chemicals and materials that are required for the materials and chemicals and materials required for the fabrication of the materials, in different sensor organizations. Right. So nanotechnology is a major outlet. Nanotechnology is a major outlet for central government investment. Right. So when we speak about the nanotechnology in a major output for government investment, so federal government spending in nanotechnology excluding pre-commercialization. Right. So when we speak about the pre-commercialization, the funding will be from different agencies like DARPA, ATP, SBIR, which exceeds $100 million in 7 countries. Right. So whereas this is what the red herring vaccine, where we could get around the Taiwan is generating around 111 and Germany is around 131 and Korea is around 150 and China is lagging around 200, whereas Europe is around 204 and US is around 710. Above that we have the Japan, whose major outlet for government investment. That means Japan is investing much more on these technology issues compared to other countries, like US, Europe, China, Korea, and Germany. Right, so around it is around 750, right? So this is what the fundamental case. This is what the fundamental factor where the technology has been incorporated. So Japan, if we know, Japan is the only country which is growing, which is being commercialized, which is giving a lot of technology based equipments compared to China, right? Compared to China, Korea, Germany, and Taiwan. Right, so that's why nanotechnology is a major outlet for government investment. So federal government sending in nanotechnology, excluding pre-commercializations, right? So most industrial countries have created top-down national nanotechnology initiatives. That is what we call it as NNI, for technology and economic development. So US top-down approach to nanotechnology investment with successive annual increase, right? So National Nanotech Initiative (NNI). So for the financial year 2001, it is $422 million. For the financial year 2002, it is $604 million. Financial year 2003, it is $710 million. So efficiencies if individual initiatives are centrally coordinated. Shared equipment, visibility, critical mass, hub developments, etc. Right. So when we see about all these features, the National Nano Initiative, it has been divided into NSF, DOD, DOE, NASA, NICE, and NIST, right? National Institute of Science and Technology, right? So National Institute of Science and Technology is a very vast university, technological institute, right? Where people will come with new types of technologies and new types of sciences and new types of computational features, right? Right, so there are so many materials in NIST. One of the fundamental applications where people use NIST, comes from the micromagnetics. So micromagnetics comes from NIST, right? So micromagnetics, which is a simulation tool, for OOMF devices, OOMF, Object-Oriented Micromagnetic Framework, right? So this was a versatile software, right, for the simulation of the materials, simulation of the magnetic materials, especially for the magnetic nanostructures, right? So that is what they missed around the $43 meters, around $43 millions. So DRDC and Canada can pursue technology initiatives based on the CANSHIS model. So it's a model, right? So it is a model. So CANSHIS is an international organization for the advancement of micro nanotechnologies for aerospace applications. And CANUS offers a collaborative vehicle for the coordinated investment and development of multinational MNTs between the multiple US and allied government agencies, industry, and academia. Since its founding in 1999, CANUS has created MNT advisory boards comprising over 150 of the world's authorities in various applications, right? So CANUS is an international organization for the advancement of micro and nanotechnologies for aerospace applications. CANUS offers a collaborative vehicle for the coordinated investment and development of MNTs between multiple US and allied government agencies, industry, and academy. Since its founding in 1999, CANUS has created MNT advisory boards comprising of 150 of the world's authorities in various applications, right? So that is the importance of studying the CANUS model, right? So CANUS model. The aerospace industry has played a major role in establishing the US global technological, economic, and defense leadership in the 20th century. So 4.5% of all US manufacturing, around 7.4% of all durable goods manufacturing workers, and $58.5 billion of export, the largest next exporter of all US industries, and $154 billion industry sales very near record level. The Commission on the Future of the United States Aerospace Industry made some sober comments on the status of that industry. Right, an aging workforce is not being replenished. Right, over 6 lakh well-paying aerospace jobs were lost over the last 14 years. NASA has 3 times as many technicians over 60 years under 30. Engineering students are more likely to favor information technology or biotechnology over space. Right, so this is what the aerospace employment. So this aerospace employment is frequently decreasing, right, in thousands, right, from 2000, so 1990, it was around 120.8, 1120.8, and now into 2006, beyond 2006, around 651. That means an aging workforce is not being replaced. That's what. Over 6 lakhs well-paying aerospace jobs were lost over the last 14 years. NASA has 3 times as many technicians over 60 years under 30. So the commission on the future, the commission on the future of the United States aerospace industry made some sober comments on the status of the industry. An aging workforce is not being replenished, right? Over 6 lakhs well-paying aerospace jobs were lost over the past 14 years. NASA has 3 times as many technicians as over 60 and as under 30. Engineering students are more likely to favor in infotech or a biotechnology over aerospace applications, right? So this is what the aerospace employment. So earlier in 1990s it is around 1120.8, and now when it comes to 2006, so it is 1641, and beyond that there is a chance, there may be a chance of decreasing of the aerospace employment, right? So the Commission on the Future of the United States Aerospace Industry made some supplements in the status of the industry also. So this is what the aerospace foreign trade consolidations have reduced competitiveness. In the past decade, over 50 US companies have consolidated into 5. Aerospace foreign trade of US companies has subsequently dropped. The Commission on the Future of the United States Aerospace Industry made some more sober comments on the status of the industry also. Over reliance on and inefficiency in government programs, US aerospace industry overly depends on major government programs for the revenues. Giving the high budget defeats the changing political objectives and public opinions from current events. Many long-term defense and space programs run on the risk of applications. So these use US aerospace R&D funding by source, right? So this is what we can see here. So this was quoted in billion, and we have taken from our website. Right. So MNT platforms are the lowest common denominator in aerospace and aerospace end technology, end products. So we have sectors called civil aviation, space, national. End products, we have commercial aircraft, general aviation, civil helicopters, and air traffic controllers, spacecraft, satellites, rovers, ground controllers, military application, military helicopter missiles. And systems, we have flight deck fuselage, turbines and engine propulsion, landing, navigation, communication, information management, safety, robots and safety robotics, weapons. And where the components, we have the structural, electrical, mechanical, optical, biological, man-machine interface, and avionics, computers, data storage, energies, right? And we have the material platforms, device platforms, and we have sensor platforms, energy platforms, and we have the life support or medical platforms. So these are platforms, the lowest common denominators of aerospace and application and products. Nanotechnology has the potential to provide the aerospace industry and collective process for providing new platforms with predictable release dates that have better performance, increased functionality, better reliability, and lower unit prices. So this is what we have. This particular structure. This is what we have some features, right? So these features distinguish it from material platforms, device platforms, sensor platforms, energy platforms, and life support medical platforms, right? So as we told that Canis model applies to multi-phased approach to transition MNT concept and prototypes to system and ventures. So we have different phases like phase 1, phase 2, phase 3, and review of current status. Phase 2 represent the plot project selections, and we have plot projection and prototypes, right? Where we have the aerospace systems for the public sector, and we have aerospace systems for the private sector, and sync of products where the materials, devices, and systems and technology energies. So this is what the pre-conference. This is the conference level, post-conference, and this is what the manufacturing. So when we speak about the manufacturing products, so we have aerospace systems for the public sector in phase 4, right? Aero systems for the private sector, and spin-off products, right? Spin-off products. So these all comes in the manufacturing units. So funding objectives for to establish an investment platform for financial Canis micro nanotechnology from concepts and prototypes to systems and ventures with investments from the public and private. So this is what the graph that is shown. Everything is shown in dollars, right? So concept papers from sponsors, pilot projects, prototyping from multiple government agencies, full-scale development from venture capital, commercialization from aerospace private sector, and this is what is private sector. So implications of nanotechnology to DRDC. and Canada. Nanotechnology has the potential to develop the next generation technological solution. Canadian challenges such as peacekeeping, border security, and biothreat early warning systems can benefit from innovation employment technology and other technologies. DRDC funding can be leveraged by additional funding from other federal and provincial agencies. The private sector and the allied countries through census type initiative, right? So this can reduce the time to market for new technologies and stimulate economic development in Canada. So that is what the nanotechnology has the potential to develop the next generation technological solutions. Canadian challenges such as peacekeeping, border security, and biothreat or early warning systems can benefit from innovation, employment, nanotechnology, and other technologies. So DRDC funding can be leveraged by additional funding from different government agencies, right? Government and professional agencies. So the private sector and allied countries through a census type initiative. So this can reduce time to market for new technologies and stimulate the socio-economic development in Canada. And finally, we can conclude that this is what the target is as we are nanotechnology broad applications. So we are enabling technology, small, light, incredible performance platforms, subsystems, and revolutionary military applications. That's all. Okay. So this is what the implications. The implications of nanotechnology DRC in Canada is the most important factor that you need to understand.
Like, share, and subscribe. Hit the bell icon for more updates.